In this video, we talk about how to recognize that our model is truly linear, and then how to build it and use it to make predictions. Let's get started. To begin, I wanted to remind you that to be a linear model simply meant that your average rate of change between your y-coordinates, your outputs, for a fixed constant number of inputs, or x values, has to remain constant. If that's true, we say that we have a constant rate of change known as slope, where slope was really your rise over your run, or your change in y values, y2 minus y1, over your change in x values, x2 minus x1. So we'd say this is when we have a linear model. So a function is linear, our model is linear, whenever the rate of change between consecutive outputs is constant. Okay, that's a very specific phenomenon, and when it happens, the model is incredibly easy to set up. So let's give an example from real life as to when we might have a linear model. Here in my blurb in the middle, we see that we're talking about a 50-gallon tank, which is initially full of water. But it's being drained at the bottom of the tank, maybe there's a hole, and it's being drained at a constant rate of 10 gallons per minute. So every 1 minute, there are 10 gallons fewer. 1 minute goes by, now we only have 40 gallons. 2 minutes go by, now we only have 30 gallons. So it's decreasing at a constant fixed rate. So the question is, how would you be able to write the model that describes a situation so that if you knew how many minutes have gone by, you know exactly how much water has left the tank? You also know when will be empty, right? Now this one is so nice and easy that I'm sure you already know the answers even without writing the model, right? However, because we're going to get more complicated models later in the course, it's important that you take the time to write down the model and then use it to make the prediction. So you have a trail to leave behind, how you thought the process through. So here what we're doing is we're noticing that because we have a constant rate of change, we have a linear model. And to write a linear model, like we mentioned above, we write y equals mx plus b, where m is your slope and b is your y-intercept. In other words, your slope could be understood as your constant rate of change. So in my function, that's why we're making negative 10 gallons per minute. We're making that our slope. And that's because we're going down 10 units every 1 minute. Down 10 units every 1 minute. That makes sense then when we look at our equation here in our graph. We're going to start at 50, go down 10 every 1 minute. Our slope is constant, so we do it again. We go down 10 every 1 minute. Okay, so that's the idea of a rate of change which is negative and it's fixed. We also notice that since we started at 50 gallons of water, that would be our y-intercept. Your initial amount is always your y-intercept. Your constant rate of change for a linear model is always your slope. So once you understand that, setting up a linear model is incredibly easy. You can now answer any question like, when would a gallon only hold let's say 20 gallons, right? You could put 20 gallons on the left, and you could then solve for x, right? I could ask you a question about at this x value, how many gallons are in the tank, right? So any of those types of questions. I could give you an input, you could give me an output, and vice versa. So that's the beauty of a model. Now, in real life, what typically happens is we're not just told what the constant rate of change is, but rather we have snapshots in time, right? At this point in time, this is how much was there. At this point in time, this is how much is there. And we usually can graph our data. So like in the slide at the bottom right here, we graph our data with scatter plots or points, and we try to analyze what's going on, okay? What is the likelihood that something in the future will happen like this? And so if you notice that your scatter plot reveals some type of growth or decay, which appears to be linear, what you can actually do is a process called linear regression. I'll just say REG for short. Linear regression is a type of regression analysis that we study usually in a statistics course or higher mathematical classes. And we actually give you the skills in those classes to be able to find the model that best fits the data, which is very, very powerful, to then be able to use technology and make predictions. So what we're going to notice later on today is I'll open up one of those types of technology like Desmos.com, and I'll show you how technology could help one to figure out the model that best makes sense. Okay, so let's continue with our discussion of linear models in our first example, where it says you pay an activation fee and a monthly service for your cell phone. This sounds about right in America. Typically we do have a monthly plan and we do have to have an activation fee unless for some reason we get that waived, right? So we pay an activation fee at front one time, and then every month we pay an additional monthly fee. So it says, use the table below to answer the following questions. Now let's look at our table. In the first row of this box, we see that the months of service are given. So after 2 months of service, below it, it tells us how much money we've spent, our total cost in dollars. So after 2 months of service, I've spent a total of $137. Now remember, that would include the activation fee plus 2 months of monthly service fees. After 4 months, I spent $209 altogether. After 6 months, $281 altogether. 8 months, $353. And after 10 months, I've already spent $425 on this phone. Now, we usually don't think in terms of the total amount of money that we spend per year. We usually think on a monthly basis, perhaps. But this is a good way of analyzing over the whole year how much we're really spending on this thing. Okay, so let's take a look at the first question. They ask us, explain why this situation could be modeled as a linear function, and then find that equation. Okay, so if it's really a linear function, what type of equation am I looking for? Yeah, that's right, y equals mx plus b. So that's what we mean by a linear function. So if it's truly linear, we are looking for a slope and a y-intercept. That would be the situation. But we're going to have to actually find the slope and the y-intercept that represents this function if it's truly linear. So how did we determine if a function is truly modeled by a line? Well, by noticing if the rate of change is constant. So that's the key. Do we have a constant rate of change between consecutive outputs? In other words, do we have a constant slope? If so, it is in fact linear, right? So to figure that out, we remember our slope formula for the slope between 2 points is y2 minus y1 over x2 minus x1. So if we picked consecutive outputs and inputs, right? For example, 2, 137, that's one fixed location, and then 4, 209, that's a little bit higher, another location, we could get the slope in between them by subtracting our y values, y2 minus y1. If you do 209, for example, minus 137, you're going to get a certain number. And if you do 4 minus 2, you're going to get just 2, aren't you? It turns out here we get, I believe, 72 in our numerator. And dividing that by 2, we get a slope of 36 over 1, or just 36. That means that every 1 month, we've paid another $36 total. Okay, so as far as that's concerned, we found the slope between those consecutive outputs, right? But what about the next 2 consecutive outputs? If you were to subtract 281 minus 209, what would you have gotten? 72. And 6 minus 4, x2 minus x1, also 2. You're getting the same slope. If you do the next consecutive outputs, 353 minus 281, you get 72 again. And 8 minus 6 is still 72. So it's still 2. And so you get 72 over 2, which is still 36. Same slope. And finally, comparing the last consecutive outputs, 425 minus 353, you still get 72. And 10 minus 8 is still 2. So 72 over 2, the slope is constantly 36. If this happens, after checking consecutive outputs, you're getting the same slope each time, you truly have a linear function. We happen to have also stumbled upon our slope, haven't we? Yes, we have a constant slope, and that is our slope of 36. So every 1 month, we have increased the amount of money we've spent on this phone by $36. Okay, so what does that mean? That must be our monthly, yep, that's our monthly service fee. You just found the last question already. Our monthly service fee must be $36. I'm going up by $36 every single 1 month. So that's found. But the next question is, if you wanted to answer the question about what is the whole model, right? You now know that your cost, you can maybe use C of x for cost, that's your output, right? Equals 36x plus something. What is the something? Well, wouldn't that be the initial amount that you would have spent, right? Your y-intercept. So that's also known as your activation fee. B is your y-intercept, and your y-intercept is when you let x equal 0 typically, right? When x is 0, that would mean when you haven't actually used any months yet, you've just paid your activation fee, how much did you have to have paid? Well, if we think about this, we could go to our graph and we could see it that way. But if we understand that each 1 month you're going up by $36, you could have noticed that at month 2, you've paid a total so far of $137, right? So what would have happened 2 months prior to that? You could go 1 month, but 2 months prior to that would be when x equals 0. 2 months prior to that, you would have had to say, I start at 137, that's how much I've spent after 2 months. What would have been 1 month before that? $36 less. 1 month before that, $36 less. In other words, $72 less. And when you do that, when you subtract your 137 minus your 72, don't you get $65? So what we're claiming is that your y-intercept, your activation fee, should have been $65. In other words, 36x plus 65 gives you your output for how much you've spent total on the phone every 1 month x. So that should make sense, especially when we look at our graph. So let's do that. Let's head over to our graph and see if this makes sense. So in this graph, what I've done is I've actually plotted some points. And if you wonder how to do that, in Desmos.com, for example, you can go to the plus arrow here and then click table. And when you do that, it'll allow you to input your x values like I've done, 2, 4, 6, 8, and 10, and your y values like I've done. Notice that they automatically will name them x1 and y1, so they're specific x and y values. We can see that on the graph, those values have been plotted in black dots, and they do appear to be growing in a linear fashion. We could draw a line through that. Now, the line that we found ourselves was 36x plus 65. So look what happens when I draw that line through those points with the blue line there. Yeah, we see, in fact, that line goes perfectly through those dots. So if we had done the arithmetic incorrectly, it wouldn't have been the same line. It would not have gone through those dots. Now, if you wanted to find that line without doing the math like we did, we thought about the slope, and we used the slope to answer our questions, including the y-intercept here. By going down 72 and left 2, we ended up getting 65 for our y-intercept. But you could have also asked the technology to do the regression for you by putting in the table and then saying, calculator or Desmos, can you find me the approximate line that goes through these points? The way you do that is you take your y value, which was y1, and instead of setting it equal, you use a little tilde, like the squiggle, and you say squiggle, or tilde, mx plus b. But instead of x, you write x1, since that's where the x values you were using come from. What this will do is it will tell you, first of all, how accurate your line is going to be. Whatever that number r is your correlation coefficient that you'll learn about if you study statistics. And basically, the closer r is to 1, the closer you are to being 100% accurate going through all points on the line. Notice r equals 1 in this case, which means our line should go through every single point perfectly. But if we had some scattered points along the way over here, if we had some scattered points all over the place, that would indicate to us that it's not a perfect fit, but it's the line of best fit. So the closer to 1, the better. Notice also it then gives you your M, 36, and your B, 65, which is exactly what we had found the long way. Okay, so that's an example of a linear model that we built by recognizing that, in fact, we had a constant rate of change, and then we used slope to find the y-intercept. Let's head over to our second example of the day in our slide here. This one involves purchasing a car. Okay, so suppose you decided you were going to buy a brand new car. And you bought a brand new car for $20,000. I did this when I was young. I got my first full-time job, bought my first brand new car. I was so happy. And then I realized how fast it lost value. Yes, very sad. So this is called depreciation, when you lose value. Appreciation obviously means when you gain value. Antiques are examples of gaining value over time. Okay, so if you bought a new car for, let's say, $20,000, and we're told that it depreciates using the straight line method, meaning linear model, right? Straight line method. It's going down in a line. Over 10 years, when they tell you the amount of time it takes, what that's saying is the amount of time before your item, in this case your $20,000 new car, is worth 0. So this is when it is worthless, or worth $0. Okay. So I could go to my graph now and visualize that, right? Suppose I let each tick mark here be worth 5,000 just for the sake of convenience. So 5,000, 10,000, 15,000, here's my 20,000, let's say. Okay, so maybe that's where I start off with my car at $20,000 in value. My blue dot there. And we're saying that over 10 years, if we go by ones for our x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, after 10 years, this is 10, my car is worthless. Okay, sad day. That means then, using the straight line depreciation that they're describing here, we would have something like, let me see if I can draw a straight line today. it's pretty okay. All right, not perfect, but okay. We'd have something like that going on, right? For example, after 1 year, my car is worth a little bit less. After 2 years, a little bit less. Maybe around 4 or 5 years, we're around the halfway mark of its value, okay? So we can kind of see what's going on based on drawing a picture. That's always a really good idea for problems. Can you draw a picture to describe the situation? The next thing I'm going to do is come up with a linear model that describes the picture. So to come up with my linear model, we could say that the y-axis was your value, so value V, and that's in terms of dollars. And we could say that the x-axis is your amount of time, right? So the x-axis is your time, and it's in terms of years, every 1 year. So here's what we have, right? If we're trying to write our equation for value then, we would say that the v of x value depends on your time, x. And for a line, if it's truly linear, we have a constant rate of change, so we have a slope that we're going to need to find, times our x, and we have an initial value that we had, which is our y-intercept. That's always the setup for a linear model, mx plus b. So the question is, do you know either of those pieces? Do you know the constant rate of change, and do you know the y-intercept? Well, the easiest is the y-intercept in this situation, because in fact, the y-intercept is the initial value, and we can see that on our graph right there, right? 20,000 is where we begin. So that would be our y-intercept. So our y-intercept b, is always our initial value when your x is 0. That's why it's your initial, right? When x is 0. Okay, so we have that part of the model. What about the slope? You can kind of visually see it, right? You're going down by 5,000 every 1 year, it looks like, according to the way I've drawn it. So down by 5 every 1 year. Okay, so how would you have said what's going on in general? Well, you could have noticed that in general, you went down $20,000 to make it valueless after 10 years. In fact, if you were thinking of rise over run, you went down 20,000 every 10 years. So in 10 years to the right. So what does that mean if you go down 20,000 over 10 years? Well, that would mean that you'd have a negative slope, wouldn't you? And 20,000 divided by 10 is 2,000. So what that's saying is I'm going down by 2,000, not by 5, like I accidentally misspoke a moment ago. It looks like I'm going down by 2,000 every 1 year, 2,000 every 1 year, etc. So if I'm going down by 2,000 every 1 year, so that after 10 years I've decreased to 0, this would mean my slope is negative 2,000, right? So my equation that models the value of my new car, depending on how many years I've had it, would be negative 2,000x, where x is the number of years I've had it, plus $20,000, where I initially walked out of the car lot paying. Okay. The second question they ask us is, what is the implied domain of this function? Now, implied domain is an interesting concept. We know that for a line, if the line were allowed to continue to the left and to the right forever, its domain would be all real numbers, negative infinity to infinity. But the implied domain is related to the word problem at hand. In this word problem, the line isn't allowed to go on forever because I'm only interested in the value of the car when I first buy it, when x is 0, and when it's valueless, 10 years later. So I'm only interested in the x values between 0 and 10. So the implied domain would be 0 to 10 in brackets. Those are the only times I'm interested in this line. Third question says, what would the car's value be after 4 years? So this is an older question, right, from our previous math classes. We know how to input a number into a function and get the output. That's all it's asking. What is the car's value after 4 years? In other words, please find v of 4, the y value when x is 4. You can do that by taking negative 2,000, multiplying it by 4, and adding 20,000. So you get your negative 8,000 plus your initial amount that you paid, 20,000. And now we see, you probably could have figured this out without the model, I know it's an easy one. You see that you have a car after 4 years, which is now only valued at $12,000. Okay, kind of depressing, okay? But maybe you're interested in selling the car once it's only worth $5,000. When would I need to sell it? That's what we ask you in question D. So in question D here it says, when will the car's value be just $5,000? So we would actually want to set value, the output, the y value, equal to $5,000 and solve for x. Go ahead and do that. Feel free to pause the video and see if you get the same result. So if I were to solve this for x, I would have moved my 20,000 perhaps to the left side by subtracting it. That would give me negative 15,000 equaling negative 2,000 x. Then I would have divided both sides by whatever is touching x. So dividing both sides by a negative 2 grand means you're going to get a positive 15 over 2, also known as 7.5. So 7.5 years. So after 7.5 years, I expect my car to only be worth $5,000. And maybe that's when I'm going to sell it because I want to make some money on it, not be worthless. All right, so what we've done in this video is we have discussed how to first recognize that your model is linear because you have a constant slope or constant rate of change between consecutive outputs. And then we talked about how to then build the model using the slope and the y-intercept to then make predictions. I hope this made sense. Feel free to watch it again and make sure to practice because math is not a spectator sport. I'll see you next time.